Okay. Okay, good. Let's go ahead. I think that's valuable in summary because.
Yeah, I think so. Yeah. So we were saying that, like, in classical computing we have either 0 or 1, and in quantum computing, a qubit it has both states with this both states happening at the same time with this state, which also uses complex numbers to define the amplitude. So at the end, we were saying when we try to measure a qubit, it will collapse into either 0 or 1. So so why it's different than classical computing. The thing is, we can make computation taking advantage of those of the superposition, but at the end we can measure it, and we will see why the phase of those complex number is very important. So one characteristic, if we are measuring a qubit, it's like a qubit will collapse into state 0 with a probability of the amplitude of C0, the square of the amplitude of C0, and will collapse into 1 with a probability of C1. I'm sorry, there is a mistake there. It's C1. So it means if I start measuring a qubit like 100 times, I will get a certain percentage of zeros and the other percentage of ones, according to the amplitude. According to the amplitude of those complex numbers. So let me show you just two examples of what a state of a qubit could be. The first one is this. So I have those are complex number with the imaginary part equals to 0. So still those are complex numbers. So if we rewrite this vector into direct notation, we will have this this number. So if we compute the probability for each state, it's 50% for the state 0 and 50% for the state 1. Another example is the one below. This one, this vector has a complex number in the second for the state of 1. And so it means that from the point of view that measuring, both are equivalent.
Yeah, Cristhian, we have a trouble to hear you right now. Suddenly, your microphone just dropped.
Okay. Check. Yeah.
Okay, now I think it's okay now.
My headphones got disconnected. Can you hear me now?
Yeah.
Okay, awesome. So I was saying, for measuring purposes, both qubits are equivalent for both states, and like I mentioned before, the phase of each complex number here for C0 or C1 will be is going to be important when we are doing computation. So I'm not sure if anyone has a question here. Is it clear? Yeah. So basically, I showed the definition of a qubit based on two states, 0 and 1. So as you probably remind, complex number also has the Euler notation. So we can rewrite these both numbers C0 and C1 with the Euler notation. So if we rewrite everything again, we will have something like this, where R0 is the amplitude for C0, phi0 is the phase for C0, and so on. So like I mentioned, phases are going to be important in computation, because if we move phases, we'll be having different complex numbers. And the amplitudes are going to be important in measurement, which, like I said, we will find out that several states are equivalent from the point of view of amplitudes. But when we measure them, we're going to complete a certain task in quantum computing. So if we, again, both qubits on the previous slide, I rewrite in the Euler notation. So here are both. The first ones, it didn't need any change, but the second one, it has a phase of pi divided by 2. So we can also write down the states in that way with the Euler notation, which is going to be useful because this is going to be really helpful tool when we try to visualize what's happening or what's happening with a qubit specifically. So if we start doing a transformation to that state. So if we divide the state by e to the I phi 0, we're gonna get this. Divided by a complex number of module 1, it doesn't change the module of the qubit. So we can say this definition is equivalent. But this is for, I would say this is for visualization purposes, because the value of phi0 and phi1 are important. So as we defined it before, the square of the amplitudes, the sum of the square of the amplitudes are equal to 1. So we can rewrite like R0 as cosine of theta and R1 as sine of theta. So then we can have a notation like this. So if we see the notation, we only have 2 parameters, which is theta and phi. And there is a visualization tool, which is called Bloch sphere. So we can visualize the state of a qubit in that way with theta and phi. This is quite useful because we can see how certain task or certain operation is changing the state of a qubit, either on the value of theta or the value of phi. So theta is defined from 0 to pi, and phi is defined from 0 to pi. Yeah. So the second figure shows that if we visualize the same latitude of those qubits in the same latitude, like this circle, we can say that the probabilities of those qubits are equivalent, because it depends on the module of cosine. Yeah, it depends on the value of cosine and sines. It means it only depends on theta. So even if phi changes from 0 to pi, the probability of measurements are still same value. So those qubits are equivalent. Yeah, the Bloch sphere doesn't change the phase of either C0 or C1. These transformations is only for visualization purposes, I would say.
Okay, Cristhian,
Yeah.
so for the previous slide, whether this is this?
I'm sorry. Oh, no.
It looks like
liquidity
it
states
is because
satisfied.
this.
These are different.
So it could be.
That
Yeah,
this
this like 45 degree, and so that's half. Oh, so this should be here.
yeah, and
That's
latitude 0, we could say.
Mhm. I see.
Yeah, and yeah, and
Where is
fact is that
this? Where is this?
yeah, it's rotated pi divided by 2. So it means if the phi1 is here,
Mhm.
it's minus phi should be to the back.
Okay.
So it's rotated minus pi divided by 2. So this
By
could be
90 degree.
this. Yes.
Okay. Yeah, it's
90 degree.
okay.
Yeah, so it's really helpful when we start learning about quantum computing, when we start playing with those parameters, so we can understand what certain operations are. So let's move to the next slide. So like I said, we can do certain operations. We can move around the z-axis, move around the y-axis, or we can just move or change the value of theta in order to change the probability, the output probability of the qubit. So we can start playing with it. So let me define a transformation matrix for a qubit RC, which is going to be the a rotation of theta around the z-axis. I understand this is quite confusing because this should be another notation. Yeah, because this theta is different than this theta. Yeah. Yes, it's going to be complicated if I start changing right now. So this transformation matrix is a rotation of theta value around the z-axis, like this, like the second figure. Is we're going to rotate the qubit around the z-axis. So we can just do the multiplication matrix between RC and phi and the state phi and the qubit state, just like any other multiplication of two matrices. So we get this, after the multiplication, we get this new vector for the qubit, for the new qubit. And if we start doing the transformation we did in the previous slide for the block sphere, we can get this notation. So what does it mean? So the cosine, the amplitudes are still the same. So it means that it's at the same latitude. It's still at the same latitude. But theta changes, the phase changes by the value of theta. I'm sorry, I know it might be confusing, but the theta in the cosine and sine are different than the theta of the rotation. Just I made a mistake in the definition. So it means that it means that we rotated the qubit from this point a theta value around the z-axis, like it could be, it could be the case in the figure, in the second figure. So we also can still perform other transformations, like I mentioned before, rotating around the y-axis. or the x-axis as we can define in these two transformations. Just to point out, the gates the transformations in quantum computing are unitary operations. So it means that the modulo of that matrix is 1. And all the gates that are not measurements are reversible. So it means given an output, I can given an output, I can still get or reconstruct the input. Yeah. So don't know if anyone has a question so far. Okay, I think we're going good. We are going good.
It's a very good summary and covered a lot of things. If people understand this, so it will be a good summer course, actually. But of course, it will take much longer to explain this. But the concept is because we have this three-dimensional sphere, so you need to have this complex system with two complex numbers to describe the direction and the phase of the qubit. So nothing fancy, but it's just a convenience way to mathematically describe the direction and the angle, and that's it. Yeah.
Yeah, I would say the most fancy thing here is the denotation. We will see that like we still we move on the notation of the qubits on this stage are really interesting. So next slide is I mentioned that gates are reversible. So let me talk about a little bit what it is. So in classical computing, we have NOT gate or AND gate. So we can taking advantage of the definition in the first slide, we can define a NOT transformation, the matrix, the transformation matrix for the NOT gate as this. So if we have an input of 0 in classical computing, remember we only have 0 or 1, and we can still perform the transformation in order to get the output. So the NOT of 0 it's 1. It's well known or well understood, and if the output is 1, if the input is 1, the output is 0. So if I know the output, either it is 1 or 0, I can still reconstruct or go back and get the input. So the NOT gate is reversible because given an output, one can determine the input. But an example of non-reversible gate is the AND gate. We know that for the AND we need 2 inputs. I would say bit 0 and bit 1, and we will get just an output. So we can still have the transformation matrix for the AND operation. And if we have an input of 1, 1, it means that the output is 1, right? And if we have an input of, let's say 0, 1, the output will be 0. That's and for 1, 0 and 0, 0, the output is 0. So that's how an AND gate works. So it is not reversible because given the output of 0, we cannot determine the input. It could be 0, 0, 0, 1, or 1, 0. So those are examples, or those are examples about what reversible and non-reversible operation is. So let's move forward and talk more about gates. I'm sorry.
Cristhian, if you go back, you may have a typo maybe here. So this is 1, 1. That's 1, 1. That's correct. But here, you certainly this should be 0, 1. Is this a 1, 1?
No.
So this should be 1.
Yeah, this is 1, 1. This vector is 1, 1. No, and this vector is
1 should be 0, 1, 0, 1, right?
No,
No.
no. The 1 state is let me
Okay,
write
correct.
down.
Yes. Okay.
Yeah.
So
For
1 should be 0 1.
yeah, it's 0 0 0 1
From
1 0 and 1 1. Yeah. So that's the way we are defining here. I will explain that how now have
Okay.
having two inputs we have a vector of dimension 4. I will explain later. Yeah. So let me. I will remove the type. Yeah, we change it. So yeah. So, but I think it's yeah, I think it's clear, right? What a reversible and non reversible a gate is. So let's move forward and talk about a little bit gates, which is basically the definition for an operator. So like I have shown before, we have those kind of things like rotating around z-axis, y-axis. Those are operations or transformations. So a gate is an operator that acts on qubits, and a gate on a single qubit is a unitary matrix. Like I said, is the modulus 1, and they also have this this property that G. What's the name of this symbol? G cross times G equals to identity. So just the definition, G cross is equals to the conjugate, the transpose matrix of the conjugate of G. So this is, I'm going to show an example about a gate of 2 dimension, of 2 qubits, which has a dimension of 4 by 4. So I will show the controlled NOT gate, which it has a shortcut C naught. It has 2 inputs, X and Y, and 2 outputs. One of them is X, and the other is the NOT. And that this NOT operation depends on the value of the X. How it depends on the value of the X? Okay, we can go to the right, and let me show you. As an input of 0 0, the first qubit is going to keep the same value, right? So there is, in the output, it doesn't change the first column. And for the second qubit, if the first qubit is deactivated, it means 0. The output wouldn't change. The second qubit wouldn't change. So it means for 0 0, the output is still 0 0. So the first qubit here is the first input, and the second qubit is the operation, which since the input is 0, the first qubit in the input is 0, the operation is not performed. So still this one is 0. Same here. The first qubit is 0 and the operation is not performed in the second qubit output. But if the first qubit is 1, the operation is performed in the second qubit. So we have, since this is a control NOT, we have 0 changing to 1. So, and also from 1 1 changing to 1 0. So that's the control NOT gate, and this is the transformation matrix. So we can perform that operation for any state we have, like 1 1. This is the matrix. This is the transform matrix, and this is the vector matrix. The vector. So if we perform the operation, we get 1 0, like in this table, similar as the table, and same for the second example. So I'm not sure if everyone got the idea why we are still keeping X and performing the operation. That's a keeping. I would say keeping keeping one input of those 2 qubits will lead into how should I say, keeping one of those qubits will lead into that the operation is reversible. We will see later why. But I think that's the idea. In a gate we have certain task. That task has a transformation matrix, and we can perform that to the vector state we have. So we will have an output. So to move ahead, I need to define what a tensor multiplication is. The tensor multiplication is an operation, and this is the definition. Is basically replicating this second matrix into the first matrix and multiplying by the values in the first matrix. So it's another transformation, I would say, but we can see the dimension of the first matrix is 2 by 2, and the second matrix is 3 by 2, and the output it has a dimension of 6 by 4. So the matrix, the size of the matrix increase very fast. If we multiply another, if we perform another tensor multiplication to this matrix, it will also increase really fast. So that's one thing in quantum computing and in quantum mechanics too. The tensor multiplication increases the vector space really fast. So that's why classical computers cannot simulate quantum systems. So if we perform the tensor multiplication of let's say just 5 qubits, so it will have a dimension of 32 by 32, which is actually a huge matrix. And if we keep going like 10 or 20, it increased almost exponentially. So yeah, that's why basically we cannot simulate quantum mechanics in classical computing. Okay, one property of tensor product is not commutative. It means that A tensor multiplication B is different than B tensor multiplication A, and we will see why. So from the definition in the first slide again, let's multiply the state 1 tensor multiplication to state 0. So we remember the state 1 has this matrix, and if we perform the operation defined on the top, we have this. We have an output like this. So it means that this is my new state for those qubits, for these 2 qubits. Basically, this operation entangled 2 qubits. Now these 2 qubits are entangled. So yeah, previously we talked about entanglement, like the last time I talked about quantum computing. So this is how it happens actually in definition and also in quantum circuits. So just a notation, which is really convenient for this kind of large vectors and huge matrices. It's like just put together 1 and 0. So 1 0 implies that we perform a tensor multiplication between the 2 qubits, and it happened that way. So if we have 1 1 1, we will have a vector like 0 0 0 1, and a notation 1 1. This is direct notation. Is really nice. Takes some time to get familiar with it, but I would say just to get familiar with it, because a lot of stuff in quantum computing it has these kind of notations. So for any state of 2 qubits, we will have a vector of dimension 4, and we can still have that notation for each possible state, which is superposition. So if we just start doing start changing the notation like this, we'll have that any state of two qubits can be expressed as a sum, as a sum of all possible combination of states like 0, 0, 0, 1, 1, 0, and 1, 1. Well, of course, C0, 0, C0, C1, C2, and C3 are complex numbers, and the sum of the squares of their modules is equal to 1. And yeah, so with this, we can now think about more qubits like 1, 2, 3, and also increase the size of the gates, the operations. So I will introduce a new gate, which is really important, because this one introduced actually superposition into quantum qubits. So the Hadamard gate placed the qubit into superposition state, which means if I start the qubit with a state of 0, and I've performed this operation with this matrix, let's see what happened. I start performing the operation, h time state 0 times state 0. We have an output vector of this 1 over root square of 2, 1 over root square of 2. So we can express that vector into a sum of two states, 1 over half for state 0 and half for state 1, which I showed this. Actually, I showed this qubit as an example in the first slide. So right now we have two states happening at the same time. From the point of view of probabilities, and we start measuring this qubit, we will have 50% of probability measuring state 0 and 50% for state 1. So this is how we can introduce superposition. Of course, there are other gates that also can introduce superposition. And if we think a little bit how to introduce superposition, it's moving. If I start with a qubit in state 0, it's just moving that qubit to anywhere in this sphere with any angle of phi. Of theta. I'm sorry. We can introduce superposition just changing the value of theta. And also we can change the phase, but we will see what happens later. So this is one of those operators. This one basically rotates the 0 qubits from C axis to the X axis. So it's a rotation, it's a changing of theta value in 90 degrees. So it's a rotation. If two or more qubits are viewed as single state, this combined state is equal to the tensor product of the constituted qubits. So it means if we start performing operation with two qubits, but I only apply this gate into one, how I can still keep working on it. So basically the new, we can say that the new gate for those two qubits is the tensor multiplication of the operation performed in one qubit and the other operation performed in the other qubit. So we can see, like, if I perform an H operation, an H gate in the qubit 0, I can also think that I am performing an identity operation in the second qubit. So identity is basically keeping the vector, keeping the state across that gate. So the new gate for those two qubits is going to be the tensor multiplication of H and identity. So the output will be H tensor multiplication to identity times the state of the input. So we can compute if we actually can compute the new transformation matrix So the H, we defined the transformation matrix on the left. So we can just perform the transformation with the identity, the tensor product with the identity, and we will get an output like this one. So this is gonna be my new transformation matrix for those 2 qubits. And also, if I start working with 3 qubits, I need to do another tensor multiplication. And if I perform like several tasks or several gates like H, identity H, I need to compute the tensor multiplication of H, identity, and H. And it works same way with any other gate. So anyone has questions here?
Yeah, Cristhian, I have a question about your the figure on the right hand side. There are two output, right? You got 2 inputs, and your output would be a combination of these 2 numbers. And my question is, why is there any interaction between these 2 parallel lines? Why the output would be the multiplication or tensor product of these 2?
Oh yeah, this tensor product is not for computing the output given an input. This is just the transformation matrix. It's like a block before a block between the input and the output. So if let's say sorry. So let's say I cannot get the annotate. So let's say I have an input of 0, 0. Okay. So I can perform this operation H tensor multiplication identity for this state. So if I want to perform this, if I want to compute the output of this operation, I just need to multiply this transformation matrix to the vector of this 0, 0 state. What is the vector of 0, 0 state? Is 1, 0, 0, 0. So my output will be 1 over root square of 2. What will be the output? It's a vector of the dimension 4. Should be 1, 0, 1, 0, first column. So this is going to be my output. So still, this is a vector. This is a state of 2 qubits, right? Yeah, my input will be right here, 0, 0.
So what's exactly what?
What kind of information? Yeah, right now I'm treating that as a circuit. Given an input, perform a transformation and get an output. What kind of information we can see from this? That's a good question. I didn't think that way, but we can think about this as that sphere with an input here, 0, 0. And we are performing a rotation. If we just check on the first qubit, the first qubit is going to rotate from the C axis into X axis. This is going to be the qubit 1, the first qubit. And the second qubit will still keep the same, because for the first one, we are performing an H gate, which, like I mentioned before, is just a rotation, and the identity gate. So there is nothing happening with the that qubit. So yeah, that's one thing we can get from this circuit. Okay. Yeah, of course. If we want to perform other kind of tasks or algorithms, being more specific, other algorithms, of course, we are not only using H, and we are using combination of several gates in order to perform those algorithms.
Yeah, for this operation, although it involves 2 qubits, but because it's 2 qubits has no interaction between them, so H and I, these 2 operation can be treated as independent. And then you just summarize at the end what the states of these 2 outcome qubit states. But if you have like a C control gate, there are communications between that, then this operation matrix like this cannot be treated as 2 independent operation on each. So you have some link between them.
Yeah, I think I have an example for a control gate.
Yeah.
Okay. Yeah, it's right here. Yeah, so let's move forward. Now we understand what a qubit is, what a gate it is. We have some understanding about how combination of gates or operations are defined. So a quantum circuit is defined as an ordered sequence of quantum gates, measurements, and resets. Also, those are operations. We'll be looking in this presentation. We'll be looking just at gates. We won't be talking about measurements. I think we have resets, or we can talk about a little bit because it's not that difficult. So I've been working with Qiskit. It's a package for quantum computing. You can actually run in a real quantum computing just using Qiskit. So there is no need to log into Quantum Compose and nothing. You can just ask for, I think, for a key, and using that key, you can directly from your computer of course, having internet, you can connect to the quantum to a real quantum computing. Yeah. So I just want to show. I wanted to show just a piece of code and also the quantum circuit for that code. So building a quantum circuit using Qiskit is straightforward if we are building a simple quantum circuit. So this piece of code shows like, okay, I import the quantum circuit class and define a new object with 3 qubits. Then I will add the H gate in the qubit 0, which is right here. And also next to that, I will add a control X gate, which is a C node from qubit 0 to qubit 1. So we have that operation in the layer 2 right here. And I also added another control X gate, a control node gate from 0 to 2. So I have 3 qubits. The first one with a rotation, the second 2 with a not operation, but those not operation are controlled. So we can think. So we can use what we saw in the last slide. So I will start explaining. First layer, we said like, okay, first qubit we can think just independently or compute the transformation matrix for that qubit. For those 3 qubits. So the layer 1, the transformation matrix will be a H matrix, tensor multiplication identity. As Dr. Cai said, there is no connection between them. So we can also think about this layer as independent qubits. But things changes when we start using control gates. So for example, for C naught, we have defined that matrix before, that transformation matrix for C naught before. So the layer 2 will be, okay, the matrix we defined it before, tensor multiplication to identity. The C naught is the transformation matrix for these 2 qubits. So I only need to do 1 tensor multiplication just with this 3rd qubit. So the 3rd layer is a little bit different because we have a qubit between qubit 0 and qubit 2. So we need to perform another kind of operation. So but it's basically the same. If it's basically like this. If we have qubit 0 in state 0, the other 2 qubits are going to be identity, right? So I perform the tensor multiplication between them. And if the first qubit is in the state 1, I need to perform the tensor multiplication of the second qubit, which is still identity because the second qubit is not connected, and the tensor multiplication to the 3rd qubit, which right now is a NOT. It's a NOT gate if the first qubit if the control qubit it's 1. So if we perform that operation, we will have a new transformation matrix for the 3rd layer. So, and if we just want to compute the whole thing, the transformation matrix for the whole quantum circuit, we just perform the multiplication between L3, L2, and L1. So we can get a transformation matrix like this one, like it's dimension of 8 by 8. And just as an example, if my input is the state 0, 0, 0, and I perform the transformation, it means if I perform this multiplication 1, 0, 0, 0, 0, 0, 0, 0, I will get an output of is the state 0, 0, 0, and the last one is state 1, 1, 1. So now I have a superposition between 2 states. Oh, and we are working with 3 qubits. Right now we are just not with 1 single qubit. So yeah, this is how like an overview how a quantum circuit works and how to understand the operation between gates. We can actually do the math a little bit. It helps a lot to understand what happened when you have more qubits and more gates. And with, of course, there are gates not only with 1 qubit controlling, no, with 1 control qubit. I found gates with 2 control qubits. We can also have 3. We can define like 4 or 5. It's up to you how far you can go. Yeah. So I think that's all about. Oh no, this is not a slide. This is all about quantum computing. Not sure if anyone has a question so far. Okay, I would say yeah, very good. We're doing great. Until yesterday, I was thinking about talk about this algorithm, Dodge algorithm, which is an algorithm using a quantum, using quantum computing. But I found out that it's quite large and it's going to be complex to follow up if we don't get this theory first. So I decided to not present this and change it and save it for the next time in order to everyone follow up or get better understanding of these slides before. So I will save it for the next time. I can show that this algorithm is really nice. Just in case, this algorithm can show us how how we can speed up in quantum computing. I would say if I have a task that requires 2 to the n times to be computed in classical computing, in quantum computing we can just compute that same task in one step, just in one time. So this algorithm is quite nice to show that kind of speed up that it's supposed to be the best advantage of quantum computing. So I decided to change it into my current research. It's unfortunate. I really hope that Yoda and Jen will take a look at this final part of my presentation. So I've been working with quantum circuits to model a gene regulatory network. So I use single cell data as an input, and I've been working on up to 6 genes, which each genes is going to be a qubit, and we are going to have a topology, a network in a quantum circuit. So as input, I'm using the log transform of single cell data. I have that data set has 2000 cells, 2000 columns, and 19 genes, 19 rows. So like I mentioned before, I'm just using certain numbers of genes. In this case, in this slide, I'm choosing 6. And so I only select 6 genes. Those are notated right here. So my new matrix is of a dimension of 6 times 6 by 2000. So after that, I perform a binarization task, which means that if the value in this matrix is higher than 1, it's going to be considered 1, and if it is lower, it's going to be a 0. So now I have a new matrix, same dimension, but I only have zeros and ones. So the pipeline works in 2 branches, I would say. The first one is labeling each cell with the value across labeling each cell by the values across the genes. So it means if I have a cell like 0, 0, 0, 1, 1, 1, the label for that cell is going to be like that, and so on for each cell. So after that, after labeling those 2000 cells, I'm going to we compute the distribution across all possible combinations we could have from 6 genes, which means 2 to the 6, which is 64 possible combinations. So the distribution of those cells, of those labels across those 64 states are like this, like it's the observed distribution from the dataset. It has a lot of zeros because not all cells has those labels. So that's why there are a lot of zeros. And the other branch of the pipeline is the quantum circuit itself. So the idea of this project is we're going to introduce or we are going to start a quantum circuit with a 0, 0, 0, 0, 0 state, and introduce a superposition with RY gates. If you remember from the presentation, I think for the second or third slide, the RY gate is like a rotation around the y-axis. So it's going to be something like this. So of course, each gate needs parameters, a theta parameters, because and that theta is the angle we are going to rotate around a y-axis. So that's the first layer, and we compute the initial values for the first layer directly from the dataset, which is the percentage of activated cells across that gene. So So yeah, this how should I say that? Each qubit has a RY gate, and that gate rotates the qubit in order to get these output probabilities. Yeah, I need to improve this figure because it's quite difficult to explain from here. Yeah, but after that, after not control RY gate, so it's like just single RY gates. We have controls, several layers of control RY gates. Those are fully connected. It means that qubit 0 control qubit 1, qubit 0 control qubit 2, and so on. And the idea of this pipeline, okay, it's like something like I have an input and I have several parameters for theta. So I get an output distribution, and that output distribution, the final goal is to fit that output distribution into the observed distribution that we got from the dataset. So there is a optimization task with loss function J, which loss function J, in order to optimize the output distribution from this quantum circuit. So as we can see in the lower part of the slide, there is a demonstration about what a observation distribution is and what a final distribution should be. So a little more details about the quantum circuit is the loss function for the optimization process is similar to KL divergence, and the gradient descent is the actual value minus the learning rate times the gradient of theta. And just in case, I also compute the error of theta, which is the difference between the sum of the square, the sum of the square of the difference of the observed probability and the output probability. So this will be a topology for the quantum circuit, like I mentioned before. We introduce superposition by several RY gates, and then we have a fully connected network between each qubit. So it means qubit 0 controls the others, then qubit 1 controls the other, and so on. Yeah, and this will be the topology for the quantum circuit in this. And I would say this can be called a quantum gene regulatory network model. So yeah, so like I mentioned before, it's an optimization problem, looking for those values that fits the final distribution similar to the observed distribution. I think I showed this table before, and I would say that the initialization of the parameters matters, or plays a role in the optimization, because if we initialize the values, we can in different ways we can still get very low loss function value and very low error. So and we found out that problem it's part of quantum circuits, and it's called baryon plateaus. Baryon plateaus says that as you increase the size and the complexity of your quantum circuit, the landscape for optimization is essentially flat. So for an optimizer, it's quite difficult to find out which direction it should go in order to optimize the parameters. Yeah, and also loss function and entanglement plays a role here in trainability. That's something I have learned from last week. Yeah, depending on how you define your loss function and also entanglement, which is those control gates. So also
you learned it from last week from the class or from the somewhere else?
Somewhere else. Yeah, I've been reading papers. Yeah, regarding to especially from this variant potatoes. Yeah. So, like I said, the best initialization for these quantum circuits will be the first one, where when we have the self regulation values, and any other value is initialized as 0. Yeah, we can still reconstruct gene regulatory network. It's quite close to the one that we know from ground truth. Yeah. So, and that's the goal of this pipeline, of this project. Have a model that can we can construct in quantum computing. It means in a quantum circuit in order to model a gene regulatory network. Yeah. So that's
Can you
it.
tell me what's this initial value is? Is it about the frequency?
Yeah,
The
this is
frequency of
frequency.
the gene.
Mm-hmm.
So that's the first layer. The first.
The first layer. Yes.
It's here. Yeah.
The one here.
Yeah. Of course, we will put that in there, and the rest of them
Are 0.
are the interaction parameters.
Mm-hmm.
Zeros
Yeah.
are they in there in here? The all zeros.
Yes.
Okay.
Yeah,
Good.
all zeros.
I think that's a reasonable setup. So we put everything 0, indicate they're very weak or there's no correlation at all.
Mm-hmm.
We just assume from the starting point. Then the search engine just try to build the correlation, the link between this and that, but in general, very sparse. A lot of them just zeros. You just don't need to put them,
Mm-hmm.
right? But the
In fact,
initial value for this
I'm sorry.
frequency, that's indication of the frequency of this at the end. That certainly will be there.
Mm-hmm.
Yeah. I
Yeah,
think that's everything looks reasonable. You start from 0 and then start to make some inference of the values and whether it's positive or negative. I think that's already enough.
Yeah.
Yeah.
Yeah, that's right. And also, I defined a threshold for the value. It means that if the final values differ to the initial values less than 10 degrees, we can just remove that connection, and nothing will happen to the quantum circuit.
Yeah. So the whole setup will shrink at the end. There's only one very strong connection remain.
Mm-hmm.
I think I like this. Yes.
Yeah, and yeah, it's really interesting. And these two things are really nice topics to discuss in the paper. So yeah, we still keep learning from those. Yeah. So that's it from my presentation today. If anyone has questions,
yeah, just want to make sure your input would be the percentage of how many ones you have in one gene expression.
Yeah, the percentage. If for example, one gene expressed 90%, then you just change the value here to make the state of this give you the high probability to be 1. And this one is only 18%. So that's somehow it's 18% become 1. So you just change a little bit the initial parameters. And we can actually fix this. We don't optimize this later. We just keep it. Is that a good idea?
Yeah.
You tried.
I've tried that first, but the trainability is really hard.
Okay, so you need to make them flexible, like it change a little bit.
Exactly. Actually, to perform these four examples, it's like 10 minutes each, I believe. Yeah, right now I would say that's because I'm using a gradient design. Not sure if I use another optimizer with you. takes shorter time.
Mhm.
Yeah.
Still have a question. So what's the output of your neural network? Still the percentage of the zeros?
The output is the probability distribution of those 6 genes. If you, well, let me use annotate. Why it's always hard to find annotate. The probability distribution, if you have a qubit at state 0, you have a probability distribution of 2 states. If it's at 0, it's 100% 0. But if you have a middle stage, like 90 degrees rotated from Z axis, you will have 50% for each. So if you start combining several qubits, you will have a space vector, a larger space vector, which is all combination possible for those states. Yes. So right now I'm using 6 genes, so I have 64 possible outputs, and the output of the qubit is the distribution, the probability distribution itself, and we are comparing that to the observed distribution, which is computed from the data set. So it means we are fitting the output. We're fitting the output of the quantum circuit to the observed distribution, and we believe that those relationships between qubits are going to be meaningful for understanding the gene regulatory network from a quantum computing point of view. That's it.
So if you have 6 genes, for example, then your output would be 64 by 1 vector.
Yes.
Okay.
Yeah, it's actually this vector. Like this is the first element, second, third. Yeah, all these values are a vector of dimension 64. Yeah. Okay. You're welcome.
And so at the end, we are not interested in this distribution because we know this. We will be interested in the values of these parameters. See, between which linker, between which 2 genes, there are larger parameters.
Yeah. Yeah. That's why this table is quite important right now, and also it tells us that we can remove certain interactions without changing the output distribution. Okay.
So by the way, you have this is the ground truth.
Yes.
So we do need to have a link between these 2 because this is one.
Yes, I would say yes.
Okay. So once you have a ground truth, then this value. So this value is normally larger than.
Yeah, it's normally larger than 10 degrees.
Okay, so we just need to confirm. Okay, this value. Once you have a ground truth, this absolute value is larger than those without link. That's enough.
Yeah.
Okay, beautiful. I think we are ready for a paper, and then.
Yeah, of course.
Yeah.
Yeah, I will start writing today. So
that's beautiful.
So I hope in a week I will have.
Yeah. I'm also thinking about this summer course. I don't know how many people will be interested in on campus, say quantum computing for biologists. Chen will be really good as teaching assistant, ask questions. Like Cristhian, you just explain and make Chen understand everything. Then we have a very good summer course. I believe.
In that case, this course will be so long because I will have so many questions.
Yeah, so you just ask questions and Cristhian answered. Then we have a summer course. I think so. Yes, from the dialogue.
Yeah.
Mm-hmm.
If it's going to be a course, I'm willing to be the TA and asking questions.
That would be really nice.
Yeah. Because I think Cristhian, the summary today is really good. It just cover basically everything. That's all you need. Then just you have to have a creative way to use those rules and play with some like a Qiskit packages. Nobody knows how to use those features actually, in the field.
Yeah, there are a lot of features.
Yeah.
Takes some time to understand.
Yeah.
And something that is going to be a new topic soon. I think there should be a book for that. It's like calculus for quantum computation. I mean, because right now there's like no stray or not much information about how to compute derivatives inside of quantum circuits.
Mm-hmm.
So that's also a topic to study, I would say.
Yeah. Okay, if we can make this 6-gene like a model procedure that can get a solution that close to the ground truth, that's more than enough.
Yeah.
Sure of this.
I have a task which is try out this pipeline with another data set, like larger, another nicer data set.
Yeah, let's start with a small paper to just put this out, and then we have other real data applications. Then we can expand and connect with other machine learning methods. But, the first step, just let people get notice that there's application of this in biology will be important. Yeah, so do it quickly. We need a quick paper, small paper for this. Okay.
Okay, sure.
Great.
Okay, we'll stop sharing.
Yeah. I will stop the recording. And it's good.